Everyone. So now we will discuss further the topic of neural networks, and we will, before we delve into more complicated or complex components, something like more powerful neural networks, more specialized to images and so on. We will focus a little bit more on implementation of neural networks. All right. So I want you to be able to understand what's going on, but as I told you already at some point, I strongly believe in understanding through implementing models and algorithms. All right, because once you understand how implement an algorithm and where are difficulties, where are these problems, so then you can truly understand what is going on. All right, so today a little bit more practical session. So this lecture probably will be a little bit faster than our previous lectures, but I want you to again to focus, play maybe this video another time or a couple of times, go through slides a couple of times, think of every single step, and try to understand everything in tiny details. All right, let's try. Let's go. First, we will look into backpropagation again, because backpropagation also requires from us, understanding how backpropagation works requires from us also a very specific implementation. And this is a foundation for developing new packages. So, what is the backpropagation, right? Last time we talked about a simple example where we had one hidden layer, so a neural network with one hidden layer. We use stochastic gradient descent to update weights of neural network. Our objective is the negative log likelihood. And we realized that, in fact, we are able to calculate gradients by using the chain rule, right? So we, here by this L, we denote the negative log likelihood. By U, we can say this is a weight. And to calculate weight, we need to apply the chain rule, right? So this is the general thing about neural networks. Please remember, there's no magic here. Backpropagation is just a name for the gradient descent and applying the chain rule, and that we can make modules out of neural network, and we can just compose these gradients according to chain rule. Okay, so how it works? So everything is basically calculating all gradients. It's relatively easy, but implementing an optimizer by hand could be very time consuming, right? Especially if we have deeper and more sophisticated models. How to understand that? So if we calculate gradient of a linear layer, it's easy, okay? It's just simple linear transformation, and for linear transformations, we know exactly how to calculate gradient. It's easy. But well, if we have a deep neural network, many nonlinearities, we need to calculate this for every single layer. We need to implement these gradients as you did in the first assignment, so by hand, everything in code. And what to do if we have, if we want to add additional layers, so should we recalculate everything from scratch? Not really. So we can notice that in order to apply the chain rule, we need to think of two operations or two steps. First is the forward pass, because for given x and y, right, we want to calculate the loss function. So what we do, so we take a neural network, we take x's, we go to a hidden layer. From hidden layer, we calculate the output, so the probabilities, and then we take the real target value and we calculate the loss. And the backward pass, we will call a backward pass calculation of gradients. Okay, so now we go, we in some sense we propagate back this gradient, this error, right, through our network. And this is actually very important because these two steps, if you think about it, so you can take one module and you can just say, all right, so I will define what is my forward pass and what is my backward pass. And the forward pass will calculate output of this layer, and backward pass will calculate gradient for this layer, okay? And let's say that we have super simple example. This is not classification, this is regression task. We have a regression model, some f of w times x plus b, so we have very simple example. And our loss function is just mean squared error, okay? And we have given x and t. So how it goes, how it works. Let's say that this is a neural network, right, with super simple structure. And how it goes. So it goes as follows. So first we calculate the linear layer, right? So we calculate output of the linear layer. Then we apply the nonlinearity to this linear layer, and we have our output y. Then we can plug it into the mean squared error, and voila. This is the forward pass. How do we do with the backward pass? This is the hard part, right? Because we need to calculate gradients. But if we realize that what we need to do, remember that the input to the loss layer, right, let's say, is y, okay? And output of this, and then of course t, and the output of this loss layer is the loss value. So then what we need to do in the backward pass, we need to calculate gradient with respect to y, because this is gradient with respect to our, let's say, input, right? Then we need to calculate gradient with respect to input to the y layer, which is just applying nonlinearity. This is just a gradient with respect to this nonlinearity f, whatever it is, right? It could be ReLU, it could be tonnage, it could be identity, right? Then, of course, we need to calculate gradient with respect to parameters of the linear layer, right? So this is what we define. And then, step by step, we can calculate everything, right? So this is actually very interesting because now you see this modularity, okay? So after watching this lecture, so please go back to this slide. Look at this model, look at this loss function, and try to calculate again everything by yourself, okay? So you can forget, for instance, about the backward pass for a second, and you will say, all right, I'm interested in calculating gradient with respect to w and with respect to b, okay? And then you will see that actually this result is correct. So this is what we have. This is the chain rule. It consists of, in this case, four calculating 4 gradients or 4 derivatives. Okay, and so this is what we will get as the final gradient. Okay, so if we say that f is just identity function, so it's just h. So then, of course, it will be simply 1, and we'll have the well-known gradient for linear regression. Okay, and maybe one thing that I didn't mention last time. So, of course, when I have this in the right top corner, we have this d of L divided by d of U, this f1, f2, and so on. So these are just exemplary functions, right? Here is the exact, in magenta, this is the exact calculation of a gradient with respect to W. Of course, if we want to calculate with respect to B, we need to replace the last derivative, so dh divided by dw, we need to replace with dh divided by db, and then of course we will have, instead of x, we will have just simply 1, right? And what I want also to say here, so when you will calculate maybe by yourself everything, so please think about modularity, okay? So please think about some kind of blocks. What would happen if I add additional block? So for instance, instead of X here, we will have another hidden layer, okay? So it will be two-layered model. Then you will see that actually it is super simple. We just add additional derivative, okay? And that's it. But then of course we want to calculate gradients with respect to first layer, so add one additional gradient or derivative to calculate, and the second layer, this will be exactly like that. Okay, so we can treat the process of calculating gradients as a composition of pre-calculated gradients, and this is a fantastic news because it means that we can very nicely define. We can write a package that will calculate derivatives for us, and this is something which is called AutoDiff, and where backpropagation is just gradient descent for neural networks, and we propagate error back from the loss function. So AutoDiff, so-called automatic differentiation, is a general way of taking some program, writing a package that will compute values and will compute derivatives of such values for us. It is an automatic procedure. Okay, and this is of course automatic differentiation. It's beyond neural networks, but of course it has a direct application to neural networks, and it is perfect. Okay, for this kind of problems. And this is a fantastic news because good news for me, for you. We don't need to bother with calculating gradients for neural networks. Someone did it for us, okay? And so AutoDiff is a procedure for calculating gradients. This is what we need to remember. But what also we need to remember, AutoDiff is not finite differences, okay? So this is a way you can check whether your gradient is correctly calculated by checking finite differences, a numerical procedure, but this is not AutoDiff, okay? AutoDiff is also not a symbolic differentiation as Mathematica uses, or Maple, or anything, MATLAB or whatever. AutoDiff is not a formula. This is not a chain rule. Chain rule is a chain rule. AutoDiff is a piece of code, okay? And it's also not magic. This is something that simply AutoDiff defines, so it requires from us to define derivatives, but then it will apply known rules for calculating gradients. If our objective function, or if our problem, our model is non-differentiable, when there is somewhere a moment that backward path is not defined, we'll get an error. Or even worse, sometimes we can get some values, but they will be not real values. Okay, so please be aware of that. And one more thing, maybe practical remark, advice. Please always think about differentiability. Okay, it requires some kind of experience, and over time, if you work more with machine learning, you will see where a problem is differentiable and where it is not. But please pay attention to that, because this is, let's say, a rookie mistake. Let's put everything into the code, just click enter, run it, and then get some weird results, okay? And then you realize, oh wow, my model is not differentiable, okay? And during this course, we'll not go deeper into AutoDiff. If you are interested, so please follow at the master level. It will be an elective course on deep learning, and we'll definitely spend more time on backpropagation and AutoDiff. But here we skip it. If you are interested, you can easily Google it, Google for it, and there is, for instance, amazing, marvelous course from University of Toronto from Roger Grosse about deep learning, and he also explains in depth AutoDiff and in general also backpropagation and so on. In this course, so we will use the the specific package, we'll use PyTorch. However, you can use other packages like TensorFlow or JAX. There are many of them, but so these are right now more and more popular, and for also educational purposes, I believe that PyTorch is the best. It's well documented, well maintained, and this is what we will focus on during this course, and we will implement neural networks using PyTorch. Okay. And now, as I told you in the very beginning, I want this lecture to be a bit more practical than usual, so that you can have a very quick intro to implementing a neural network, and we'll do it for PyTorch. Of course, don't hesitate. Please go to PyTorch documents, so PyTorch docs, and you can see examples, tutorials, and so on. Here it's a little bit like, a simple, some like minimal example that you can basically copy paste and you can play with. If you need something more complicated, please refer to PyTorch docs. And what is in general PyTorch? So we can think of PyTorch as NumPy for GPUs. Okay. And PyTorch and NumPy, they share a lot of similarities. But important fact is that if any of you has a machine workstation or laptop with NVIDIA GPU, you are in this privileged situation that you can use it and you can learn your neural networks much faster. So PyTorch provides also except this extension to GPUs, it provides also AutoGrad, so AutoDiff. AutoGrad is a specific implementation of AutoDiff. So this is for automatic calculation of gradients. But for us, in this course, it's also important not to be scared of PyTorch. And please really think about it as a NumPy. So here is a code snippet. So in this orange block, we see some super simple, generating some values, random values using Torch, and these are some numbers. This is so the idea is that every single object in Torch is a tensor. So 1D tensor is a vector, 2D tensor is a matrix, and 3 or more dimensional tensor, it's called simply tensor. Okay. And in NumPy we have arrays, and this is how you generate random numbers in NumPy. Okay, so as you can see, this code is almost identical. Very good thing is that we can also very easily import elements from PyTorch from NumPy to Tensor and vice versa. So this could be very, very simple if you have a nice code that produces something that we don't calculate gradients with respect to these variables. So then just please use NumPy code and then just pass it to Tensor using Torch from NumPy, and that's it. Okay. If not, so it's better to write everything in PyTorch. And important thing, of course, is that I said this is for GPUs. For those of you who has NVIDIA GPU that is supported by PyTorch, so it's very easy to pass a tensor to GPU. But please remember to pass all of them to GPU. Otherwise, you will get an error of a mismatch that something is on CPU, something is on GPU. In the current version of PyTorch, you can use it by specifying device. This is CUDA. And then you can just simply specify that this tensor must be already generated on device, or you can use a different additional comment that to specific device. Okay. What is better depends on your code. Sometimes it's better to define one but when you define something, you set it to CUDA. Sometimes you need to pass it manually by saying this dot to device. And what is good is that it works also with modules. So when we'll create a model, a neural network, so then you can specify my model dot to device, and then this device, if it's CUDA, so then it will be passed to GPU, and everything inside, all tensors inside will also be passed to GPU. Okay, so you don't need to do it manually for every single tensor. Right, what about gradients? So this is the main topic of this lecture, more or less, and we can specify, we can indicate which tensors are required to be traced for calculating gradients. If we define a module is by default differentiable, so like a neural network or some other model. So then we don't need to specify that requires grad true. But if we want to do that, we can do it by hand by specifying it. By default, all tensors are created, initiated with requires grad false. Okay, so please remember that. And now, what is important? It's we are getting closer and closer to building a neural network. So if we need a function that is autodiff, that we can backpropagate through, let's say, so we need to define this class. So we need to define a class, of course, of this function, and we need to inherit from a function class, general provided by PyTorch. And we must remember about specifying forward function and backward function. So remember, forward function is processing input, backward function is providing gradient with respect to input. Okay? So this is important. This is how we can define an exemplary function. So let's say that we create this autodiff function for an exponential function. Okay, so this is how it is done. Of course, PyTorch already has exponential function to be backpropagatable through, or that we can easily calculate gradients, but this is how we can do that. In this case, if the backward pass is something that is more complicated, for instance, maybe let's not go into details, but for some reasons some function is very complicated, but we still want to provide a gradient, even if this is maybe not analytical for some points, like discontinuous functions, but still we want to provide gradients, we can do that. Okay, there is no problem with that. And ladies and gentlemen, the most important class for building neural networks, module. Okay, so module, it could be a single layer, but module could be also a set of other, a composition of other modules. So module contains parameters, forward pass, and also this registers backward hook. I don't want to go into details here. This is this backward hook. This is just to remember how backward pass should be constructed in general. Okay. And let's say that we have. So if we create a module that consists of modules and also autodiff functions, so then we don't need to be worried about the backward pass. The only thing that we need to define right now is the forward pass, right? And that's why this backward hook, it takes care for calculating gradients, okay? And so on the right we have an exemplary two-layer neural network. It consists of two linear layers with the inputs, the outputs, the in, the out, and m hidden layers. And also it uses ReLU nonlinearity in the middle, okay? And then we define how we calculate, how we process X. So here we see that first we use linear layer, first linear layer. Oh, here is a mistake, by the way. It should be set linear under score 2, not 2 times 1. Then we have linear layer, and this is the output, okay? And here is on the left, we have again that what we import, what we have two-layer neural network. Here the mistake is corrected, I see. We have self-linear 1, self-linear 2. And on the right, we generate some random data, right? It is completely random. This is a random data consisting of 1000 dimensional input and 10 dimensional output. We have 64 data points and we have 100 hidden layers. We generate them totally at random, doesn't matter. Then we initialize our neural network. We define our objective function. In this case, this is mean squared error loss. We define optimizer, and the optimizer, so PyTorch also provides different optimizers like stochastic gradient descent, Adam, and other RMS prop and so on, other optimizers. Here we use SGD because this is what we are used to. And we can proceed with training loop where we define for how many iterations, epochs. In deep learning, people like to use epochs for iterations. And what we do, we take network with X that predicts some Y's. Then we compute loss function. So we have objective. We take the predicted values and real values. We calculate what is the loss. And after that, we can do something with loss. For instance, we can print it after 100 iterations or epochs. And then we need to calculate gradients, right? And apply optimizer. What we do first, we zero gradients. Due to numerical issues, due to some memory, we can have some rubbish in our gradients, okay? So we need this step. Please remember about this step. We need to zero all gradients, okay? Then we apply backward pass from the loss function. Again, let's say that the loss function is our final, this strange layer. And from this, we need to initialize the backward pass. By launching from loss function or starting from loss function, we'll calculate gradients back to the beginning of our two-layered network. And once we calculate all gradients, we just apply step of the optimizer, okay? And that's it. And then after this optimizer dot step, we will update all weights of our parameters, of weights of our neural network, sorry. One maybe additional comment, when we defined optimizer, we need to pass to this optimizer all parameters. This is what we do it by defining net.parameters. And we need to define, in the case of stochastic gradient descent, we need to define learning rate. I don't know if you remember from the second lecture that gradient descent can have this it should have the learning rate value that is decreasing. We can also add some so-called learning rate schedulers from PyTorch. If you want to learn more about it, so please go to documents. It is very well documented from PyTorch, and you can learn about it. Okay. What I presented on previous slide, I also created a Jupyter notebook. So please take a look at it and inspect it, so that you can play with that, so that you don't need to copy paste everything from this slide. So you can just take a look, as I said, play with this and see how you like it, or maybe add something new, another layer. You can replace this random data with real data and so on. Okay, and if you want to see more about PyTorch and neural networks, please go to PyTorch webpage tutorials, and then you will have really nice materials. And that's it for today. As I said, this is a bit quicker, shorter today, this time, because this is more practical. It's more on your side now to look into these tutorials and so on, and play around and see how it works. Okay, my suggestion is the following: try to keep your code clean and nice. Try to modularize everything. Please think of and please understand what is module, what is autodiff function. Try to use as much as possible what is already implemented in PyTorch. Don't try to reinvent the wheel. If you need linear layer, don't create new module. Just use linear layer that is provided by PyTorch. And that's it. I hope that you liked it, and we will next time discuss more complicated components of neural networks. Thank you very much.